Hi everybody, welcome to another video in differential equations, section 8.4, equation with analytic coefficients. So, definition or theorem. Suppose x0 is an ordinary point for the equation, then the equation has two linear independent solutions. Two linearly independent analytic solution in that form, and moreover the radius convergence of any power series is as large as the distance from that point to the nearest singular point. Right, so what is an ordinary point and a singular point, by the way? So that actually is from the previous section 8.3. So in 8.3 we have this definition: a point x0 is called an ordinary point of the equation if both p of x and q of x are analytic at x0. By analytic we mean there is a power series representation at x0. So in this case, when we say that it is an ordinary point, we mean that this power series there is a power series representation for p of x and q of x centered at x0. So ordinary meaning there exists a series representation for both p of x and q of x centered at x0. So that's what an ordinary means. So that p of x and q of x are analytic, meaning that there exists series representation for p of x and q of x. If that is the case, then the equation will have two linearly independent analytic solution of this form, and the radius of convergence is as long as the distance x0 to the nearest singular point. Singular point is opposite to ordinary point. So let me write here: singular point is opposite to ordinary point. Meaning that p of x and q of x will not have a series representation at that point, or usually if the function is undefined at that point, then it is an ordinary point. So this point, loosely speaking, we can just say p of x and q of x are analytic, meaning that they are defined. Of course, later there might be some more complicated definition between analytic and other things, but at this level we just say p of x and q of x, if they are defined, there will be a power series representation for it. Right. Now let's look at the first example. Find the minimum values for the radius of convergence for the power series solution about x equal to 0. Right, first, in order to determine if we have an ordinary point, if this is an ordinary point or not, and the radius of convergence, we have to turn that into the right form. The right form is where the leading coefficient is 1. So for this equation, I'll divide 2 on both sides. So in that case, we have y double prime plus x over 2 y prime plus 1 over 2 y equal to 0. Right? Divide everything by 2. That's what we have. Now, in this case, we have p of x is equal to 1/2 x, and q of x is equal to 1/2. Now, let me ask you this: at x equal to 0, are this function analytic? Well, that is simple, right? Because when we put 0 for x, the function is defined, therefore it is analytic. There's a power series representation. By the way, p of x, that is the power series representation for p of x, is 1/2 x. This is the power series. It's just one term, but it is still a power series. This is also a power series. Once again, it's just one term. But both of them are defined or analytic at x equal to 0. So we say p of x and k of x are defined, or we just say analytic at x equal to 0. So x equal to 0 is an ordinary point. Furthermore, there is no values for x that make p of x and or k of x undefined, so there will be no ordinary, no singular point. There is no singular point. Because p of x and k of x are defined everywhere, or analytic everywhere. And so the radius of convergence will be from that ordinary point to the nearest singular point. We don't have anything. So in that case, the radius of convergence will be infinity, meaning it is defined everywhere. Because of that, there's no singular point. So the radius of convergence it's going to be defined everywhere. Right, so this series have the solution at x equal to 0 with the radius convergent infinity, meaning it works everywhere. All right, let's look at another example. Find the minimum values of the radius convergent of the power series solution about x equal to 1. By the way, for x equal to 1, we put 1 in here. P of x and k of x are defined x equal to 1. So x equal to 1 is ordinary. But first, this will be p of x. And k of x is -2 over x minus 2. Now, at x equal to 1, p of x and k of x are defined. So x equal to 1 is an ordinary point. Because put 1 in here, the function are defined. So if x equal to 1 is an ordinary point. Right. Now we will find the singular points. Singular point is where the function is undefined. So it is analytic, or if it is defined if the denominator not equal to 0. So we solve for it, move the 1 over, take square root and plus or minus I. So we have two singular points. Here, let's just write. So we have here a singular point. Let's spell it correctly. And the second function k of x is defined if the denominator not equal to 0. So we have x not equal to 2. So we have 2 is also ordinary, is also singular point. Because when x equal to 2, k of x is undefined. When x equal to I or negative I, p of x is undefined. So we cannot write the solution if p of x or k of x undefined, right? So we have singular points at 2, I, and negative I. So if we're going to plot that on the complex plane, so this is the real axis, and this is the complex or imaginary axis. So we have singular points at I and negative I, so this will be 1, but it is imaginary, so I there, and negative 1 will be negative I. So this is the imaginary axis will be I, because opposite that negative I. And then a singular point at 2, so 1, 2. Those are the singular point. We have x equal to 1 is an ordinary point. That's what given. So this point is the center ordinary point. Now we just find the distance from that to the nearest singular point. So we have this distance here is 1, right? 2 minus 1. And this distance here. And so if we have 1 up and 1 to the left, the distance is square root of 2. So we will take the minimum numbers or the shortest distance from the ordinary point to the nearest singular point is 1. So we say the shortest distance from the ordinary point 1 to a singular point 2 is going to be 1. So the raised convergence is 1. Yeah. So when we set up the power series representation for the solution, it's going to be centered at 1, yes, but it only exists for the solution is in here. Yeah. The solution only in that circle. X cannot be outside that, because when x outside that, there will be a singular point within it. So that is the radius of convergence. Right. Now, so what we can only have is that the point has to be an ordinary point to write the power series representation for that. Later on in section 8.6, for special case of singular point, we still be able to write the solution about that, but that is the special case. Now, this is nothing special. When if it is an ordinary point, we should be able to write the power series representation for it. Right. Now the only problem is, what if it is not centered at 0? Then it will be a little more complicated, right? Right. That's why we have this. Suppose we find a power series representation for this differential equation centered at 1. Of course, we did this at the first part. X equal to mean p of x and q of x. For this equation, if we turn this equation into a y double prime plus 1/2 x y prime plus 1/2 y equal to 0. And p of x and q of x are defined everywhere. So x equal to 1, actually, when we put 1 in that, it is defined. So x not equal to 1 is an ordinary point. So in this section, we only interested in the solution about an ordinary point. Of course, in the section 8.3, we did the same thing. If it is not an ordinary point, we cannot have a power series representation for it. So we cannot use the power series unless we do some adjustment to it. But here we have an ordinary point. Alright, now the center at 1, so we can write the solution in this form. Right, center at 1. Alright. However, in terms of derivative and other things, it will be a lot easier if we use the power series centered at 0. So it is easier to work with the series that is centered at 0. So in that case, if we let x minus 1 equal to t, so we solve for x is equal to t plus 1. So we will say let y of t be little y of x. By the way, this y is just a different function. This is not a Laplace transform. Just one different function of different variable. Now x is equal to t plus 1, so we can write y of t as this series. Right. And the nice thing about this is y of t equal to y of x. So when we take derivative, it's going to be just the same. If there's 2t, different story. But it's t plus 1, so that's perfectly fine. Because derivative of the chain rule, let's say if we write y of t equal to y of t plus 1, if we take derivative, the derivative of t plus 1 is still 1. So we can say derivative of t is derivative and second derivative as well. Now, but if we put t plus 1 into x, t plus 1 minus 1, so that gives us just t. So we just make a simple adjustment like this. So now we can write the equation in terms of t. Right. So we did have x equal to t plus 1, right? So notice that here we have this x here, and x equal to t plus 1. That's why we have the t plus 1 here for that x. Yeah. So that is the price to pay when we go from from x to t. Yeah. So we have to write t plus 1 here. Other than that, it should be the same. Right. Now, the original equation becomes this. Now we say y of t is the power series, take derivative, second derivative. So this is exactly like what we have in the previous section. Substitute into the equation. That's what we have. Now we have t plus 1 times the power series. So we have t times that, t times n minus 1. So that gives us t to the n. And then 1 times that is going to be still t to the n minus 1. So pretty much multiply it out. Okay, we have 4 summation. Now we just need to combine all of that into one big series. To combine that, we either do two things. Change the index and then split out a few terms so we can combine them, or split out a few terms and then change the index. Right. So what I do here is I assume that all of them raised to x to the k power. So if we do that, the first one we have k is equal to n minus 2. If that is the case, then we solve for n. It's going to equal to k plus 2. Alright, so that is the first series. Alright, I will rewrite. Every time I have n, it's going to be k plus 2. Go to infinity. And then 2. There's an n here. That's k plus 2. And n minus 1, k plus 2 minus 1 is k plus 1, right? Yeah. K plus 2, 2 minus 1, so k plus 1. And then a of n, a of k plus 2. And then t to the n minus 2 is going to be k. Right. So we change the index. That's exactly what we did in the previous section. Next, this is easy. If we replace this to x to the k, then k equal to t. K equal to n. There's no need to do anything. Instead of n, we use k. N is going to be k. N is going to be k. and n is going to be k. And then plus. Now we want the power to be k. See if try to different color. By the way, this will be t to the k. Yeah, not x. Not x. Let's say that. T to the k. T to the k. Yeah, I did write t to the k here. Right, summation. Now k is equal to n minus 1. So in that case, what do we have? N is equal to k plus 1. K plus 1 equal to 1. N is going to be k plus 1. A N k plus 1 and n minus 1 is k. So of course we expect to have t to the k. And then finally this one we also match that to t to the k. So pretty much n is equal to k. K equal to 0. A n is equal to k, and n is equal to k, equal to 0. Right, good. Now let's rewrite this, simplify the series. 2 and 2 cancel out, k equal to 0 to infinity, 2 k plus 2, k plus 1, a sub k plus 2, t to the k, plus k equal to 1 to infinity, k, a sub k, t sub k, plus 1 cancel out, k equal to 0 to infinity, k plus 1, a k plus 1, t to the k, and k equal to 0 to infinity, a sub k, t to the k equal to 0. Right, so good that all of them have t to the k. What is not good is that this series start 1, the other series start at 0. So we have to split. So all of them have to start 1, so we can combine that into one series. So we have to split something. For this first series, we have to split when k equal to 0. So let's put 0 in here. 2, k equal to 0. K equal to 0. And after that, we can say the series we start at 1. Right, so that series start 1, which is good. The next series already start 1, so we don't do anything with the next series. Right, this series starts 0, so we have to split out one term. So put 0 in here. 0 plus 1. A 0 plus 1. T to the 0. and then the summation for that one. After we have k equal to 0, now k can go from 1 to infinity of that series. And now this star 0, we have to split out one term, so put 0 in, we have a sub 0, t sub 0, and then that series can start from 1. Right, now let's group the isolated term. We have 2 times 2 times 1, so that is going to be 4. A2 4 A2 t to 0 power is 1, so for A2. And then this isolated term is A1 t to 0 power is 1, so we just have A1. And then the t naught is t to 0 power is 1, so we just have A0. So those are all the isolated terms. And then we can combine all the power series. Factor out t to the k, so we have 2 k plus 2 k plus 1 a sub k plus 2, right, plus k a sub k and factor t to the k, so that's all we have, and then plus k plus 1 a sub k plus 1 factor out t to the k, and then plus that plus a sub k. Right, of course when we combine the power series, okay, that's exactly what we have. So we continue the note from there. Right, what we have after that is, since the right hand side 0, by the way, this is exactly what we have here. Let's check. 2 times k plus 1 k plus 2, yes, a sub k plus 2 k a sub k k plus 1 a k plus 1 a sub k times t to k. Yep, so that's exactly what we have. So if we combine series, we have this. Now, since we have 0 on the right hand side, every coefficient has to be equal to 0. So meaning this has to be equal to 0. And this has to be equal to 0. So all the coefficients equal to 0. Of course, in that case, we solve for a sub k plus 2. By the way, on the previous section, where we solve for that, when we solve this recursion, something like this, and we use the calculator, and I did mention that we can only use the calculator if the recursion only depends on one term. In this case, using the calculator will not work because we have a sub k plus 2, a sub k plus 1, and a sub k. So a sub k plus 2 will depend on this 2. If it depends on more than one term, it depends on 2 terms or more, don't use the calculator. Calculator only works if it is the relation, something like this, depends on only one term, or something like this. This term depends on that term. We do not have another a sub k or a sub k plus 1, something like that. Right. So if it is more than one term, cannot use a calculator. Right. But regardless, the coefficient must be equal to 0. So that has to be equal to 0. So to solve for A2, we have subtract A1 and A0 on the other side and divide by 4. So that's what we have. So A2 is equal to this. And then we have that along with the coefficient. Now, if we let k equal to 1, we will have a sub 3 here. And in that case, we can solve for a sub 3. Right, let k equal to 1, we have a sub 3 is equal to negative 1 over 6. So just move the a1, by the way. We have like terms here, a1 and a1. When k equal to 1, put on the 1 in here. That's what we have. a1 and a1, make it 2, move to the other side, divide by 16. That's what we have. And a2, same thing. So that's what we have. Now a2, we substitute this in for a2 and combine. Bottom line is this is a3. And then we write the power series. a0 plus a1 times t plus a2 times t squared plus a3 times t cubed, and so on. And finally, t is equal to x minus 1. So we substitute t equal to x minus 1, and we have the series representation center at 1. So whenever the center is not at 1, we should do this substitution. So when we do that substitution, the center now will be oval center at 0, and it is a lot easier to do. Right. Now in this case, coefficient will depend on 2 previous solution. So that's why we can say, yeah, so each coefficient will depend on a1 and a0. Of course, if we want to, we can split this and have a1 and a0. So instead of that, we can write the solution as we can write like this. If we group all the a0 together, 1, and then we have just that. Then we have this a0, negative 1/4 x minus 1 squared. Yeah, factor out the a0. That's what we have. And then we have the a0 here, so minus 1 over 24 x minus 1 cubed. So we can factor it out. We'll write the solution in terms of a0. And then a1, our first term is x minus 1. The next term is negative 1/4. Factor out a1, we have x minus 1 squared and negative 1 over 8. Factor out a1, x minus 1 cubed. Yeah, so we could potentially group the solution in term coefficient a0 in the term of coefficient a1, and we still have two. What did we say? We have two linearly independent analytic solution, and so those are two linearly independent analytic solution. So we can write like that. Or in terms of previously, we write C1 Y1 C2 Y2. So that is exactly Y1 and Y2, but represent as a power series. That's good. Now, before we go to the other section where we take care of the singular poles, some special case of singular pole, now we just want to do one simple example. Find the power series expansion for the solution to this. Now first of all, we have sine x and e to the x, both of them are analytic. I mean the power series defined everywhere. Once again, let's just say the center is 0. Right. So we'll write p of x equal to sine x, and q of x equal to e to the x. Both of them are defined. Both of them are linearly. Analytic at x equal to 0. So we're going to use the power series at 0. But in this case, I will not write a series. I'm just going to write a series representation. So without using the actual power series representation. Right. The solution in terms of the Taylor series. So now we will not write the power series for each one of them, but we know the solution is as follows. So we use the Taylor series. Let's just say Taylor series. Be a Taylor series S. Now, the difference between the power series and the Taylor series. Taylor series is a special case of power series. The Taylor series center x naught equal to 0. If the center is 0, we can also say Maclaurin series. But regardless, this is center at x naught. So I will just write in general form. So we have the function, write it different color, at x naught plus derivative at x naught, x minus x naught, plus second derivative. Yes, that is the Taylor series when we have the derivative. Notice that this is y, and then over 2 factorial, or just 2, x minus x naught square plus y cube, the third derivative, over 3 factorial x minus x naught cube, and so on. Notice that is the Taylor series. Of course, the power series general, we just say this is going to be a naught, a1, and the whole thing here, a2, a3, and so on. Right, so that is the Taylor series, and if we use A, that's the power series, right, in general. Right, now what do we have? Right, we have second derivative equal to that. So let's just write first we have y second derivative plus sine x times y prime plus e to x y equal to 0. We can solve for the second derivative, right? Negative sine x y prime plus e to the negative e to the x y. Right, just move that to the other side. Right, now what we have is, here we have the values of the function is equal to a naught, and a1 is equal to the values at x naught. By the way, in this case, x naught is equal to 0, so this is just 0. For x naught, instead of x naught, we just have 0. Right. So, in this particular case, we have y of 0 is equal to a naught. So we have the first coefficient, and y derivative at 0 is equal to a1. So we have a1 and a naught already, a function and derivative. Because if this one given the initial value problem, then we have a0 and a1. We are not given, so we just have that. Now, from this, if we will let x equal to 0, at x equal to 0, so y second derivative at x equal to 0 equal to negative sine of 0 y prime of 0 minus e to the 0 y of 0. Right, now we have that. So sine of 0 is equal to 0. So this one goes to 0. And y naught, actually this is y naught, derivative at 0. So it's a1. And this is a naught. The function e to 0 power is 1. So this is negative a1. Negative a1. Sorry, negative a0. Right, so that gives us second derivative. Right? Yeah. So we just solve for the second derivative at x equal to 0, and we have derivative at 0 is equal to negative a naught. Next, to get to the third derivative, from here we take derivative of that, which is a power rule. So we take derivative, and we have the third derivative equal to, now we have a power rule here. The negative derivative of negative sine x is negative cosine of x times y prime, and then plus negative sine x. Derivative of y prime is y double prime. Right, so that is a product rule there. And then the product rule here as well. Derivative of e to the x is still e to the x times y. And then plus derivative of, the first one with derivative of the second. Now, we write this at x equal to 0. So we have y at 0 equal to negative cosine of 0 times y prime of 0 minus sine of 0 y double prime at 0 minus e to the 0 y of 0 minus y prime at 0. Right, let's simplify this. We only have sine of 0 is equal to 0, so that one go to 0. Negative cosine of 0, that's negative 1. Y prime, what's that? a1 minus a1 0 minus y not y at 0 at a, and then we'll minus a2. This is derivative. Wait. This is second derivative, right? Yeah, but that goes to 0, so that doesn't matter. So minus, this is 1, y of 0 is a naught, a to 0 is 1, y derivative is equal to a1. So we can say the third derivative is equal to negative 2a1 minus a naught. Right, of course, we can take derivative, both sides, derivative of this. Of course, there will be a bunch of power rule. Product rule. But put all of that together, we can write the solution now. So, y of x equal to, first, the function at 0 is a naught. Alright. Next, derivative at 0 is a1. We have x minus x naught, x minus 0 is just x, right? So that's good. Next, second derivative divided by 2 factorial. Second derivative at 0 is going to be negative a naught over 2 factorial, and x minus 0 square, or just x square. Plus third derivative is equal to this, so we're going to substitute that in the third derivative. So we have negative 2a1 minus a naught divided by 3 factorial, which is 6. I'll just write 3 factorial for now. And then x minus 0 cube. But that series can go on forever. Right. Of course, if we just keep taking derivative like this, we can get terms by term recursively. Right. So that's why we solve the fourth derivative recursively, and then use in the Taylor series to write the solution. So we write this. We have a naught plus a1x minus 1/2 a naught x squared minus that could be 6. 2 over 6 is 1/3 minus 1/3 a1 x cubed minus 1/6 a naught x cubed, and then so on. Of course, we can write with a high power, but just keep taking derivative from here. It's not that bad. Right, so that is one way to write the solution. If we just do that, we don't have to write the power series for each one of them. Right. By the way, this is taking advantage of the Taylor series, where we have the function derivative instead of a naught, a1, a2, and a3. But that's what we have. Right. So when we write solution like this, we don't need to write the power series. Now, if we want to work with power series, then we write the power series for everything. By the way, we did this in section 8.1 or 8.2, I don't remember, but we have one solution like that. Now, if we write the power series for everything, so first of all, the problem is y double prime plus sine x y prime plus e to the x times y equal to 0. Now we will write the power series for everything, and in that case we multiply. It will get very, very complicated, so we can only need to write a few terms. Right, power series for everything. Let the function be the power series I will just write out a few terms. A naught through 4 terms, because derivative is going to be right. Now you see, that is the power series in general, as opposed to the Taylor series when we have the function derivative divided by the factorial. So that is the Taylor series. This is a power series in general. Right, then take derivative. Because I'm not even right, because let's just do that. N equal to 1, n a sub n x to the n minus 1. Or we just take derivative of this. It's going to be a1 plus 2a2 x plus 3a3 x squared plus 4a4 x cubed. That is derivative. Second derivative, n equal to 1, n equal to 2 to infinity n minus 1 a sub n x to n minus 1. right? Or we just take derivative of this. 2a2 plus 6a3x 12a4x squared I think we need a few terms here. Let's try one more. So that would be a5 x to the fourth, and then this will be 20 a5 x cubed. Yeah. So that's the power series for y prime, y double prime, and y. Now the power series for sine x and e to the x. E to the x will be n equal to 0 to infinity x to the n over n factorial so we just have 1 plus x squared over 2 factorial, or just 2, x cubed over 3 factorial, or 6, x to the fourth over 4 factorial, like that. And then sine of x is also the power series. Sine x is an odd function, so it will only have the odd terms. X to the 2n plus 1 over 2n plus 1 factorial. So pretty much the odd term only. And then the odd term only. 5 factorial would be 120. Yeah. So sine x is an odd function, so we only have the odd terms, but the sign is alternating. So in that case, I should have the -1 to the n. Right, so that is the sign. So I know e to the x have every terms divided by factorial, so all the powers divided by factorial. And then the odd function for sine, just take the odd terms, the sign alternating. The cosine function is going to be 1 minus x squared over 2 plus x to the fourth over 24, and so on. The cosine will have all the even terms, and the sign alternating, positive, negative, and so on. So that's what we have. Now put all of those series into the equation. Right, second derivative is going to be this. Second derivative, I'm going to write this out. 2a2 plus 6a cubed x plus 12a to the fourth x squared plus 20 a to the fifth x cubed. Alright. Second derivative plus derivative. But first, sine x times derivative. So I write sine x first. Sine x is going to be this. X minus 1 over 6 x cubed plus 1 over 120 x to the fifth. So that is sine x. And then the first derivative, a1 2a2 3a3 x squared 4a4 x cubed 5a5 x to the fourth, and so on. and then plus e to the x will be this guy. One half x squared 1/6 x cubed 1/24 x to the 4th times the function be that a0 plus a1x plus a2x squared a3x3 a4x4 and all of that equal to 0. Right. So like that, write the power series for everything. The power series for y double prime, y prime and y, and the Taylor series for e to the x and sin x. Now we just multiply and combine like terms. Right, let's multiply. Now when we multiply, of course, multiply now and combine like terms, that will be too much. Now we just combine every terms. First of all, do we have any constant? Constant 2a0, right? I mean 2a2. That is the only constant for the first part. If we multiply all of this out, a1 times x, and so the second series all have to have x in it, a1 times x. We cannot get the constant by multiply these two series together. Next one, if we want a constant, we have to take 1 times a0. So this is the only constant we have. a0 times 1. So that's all the constant we have. Right, now let's collect all the one with x. So first one we have here 6a cubed times x. Right, now how to get x for the second? The only thing we can get x if we take x times a1, right? So plus a1x a1 times x if we want to. And that's all we have. Next, in order to get x in this product, 1 times anything, so we have an a1x here. One times a1x and the later term will not give us x. Now we go to x times a0 also give us the x, right? X times a0 so that gives us the power of x. Now the x squared, to get x squared we have 12 a to the 4th x squared. I should write that 12 a to the 4th x squared from the first part. Now to get x squared from here, how do we get x squared from here? If we take x multiply by that, give us x. If x times that, this gives us an x squared, and that is the only thing we have. So if we take an x multiply by the 2a2x, that gives us x squared, and that's all we have. Next, to get x squared from here, 1 times that's not going to be x, that's not going to be x, but 1 times a2x squared, that will give us the x squared there. 1 times a2 x squared, right? If we use x, multiply that term, will give us x squared. If we use this 1/2 multiplied by that, also give us x squared multiplied by a naught. Right, that's enough. Of course, we can do this and we group on the cube. So let's simplify just a little bit. Yeah. So the idea is we just combine like terms. And that's what we have. Now, 6a cubed, 6a3, that's a1, and that makes that 2a1. And then a naught. Of course, we factor out the x. Next, what do we have? 12 a4. Now we have a2 here, right? a2x squared and a2x squared. They're one of them, they're two of them. Like that, 3. Factor out x squared, of course. And then there's 1x1, 1a1, and 1/2 a naught of x squared equal to 0. Next, in order to be equal to 0, all the coefficient has to be equal to 0. Right? So we have 2a2 plus a naught equal to 0. And then we have 6a3 plus 2a1 a naught equal to 0. And then we have all of that. 12a4 plus 3a2 plus a1 plus 1/2 a naught is equal to 0. Right, all the coefficients have to be equal to 0. Now this is easy. a2 is negative 1/2 a naught. So for a3 is equal to what? The 2a1 move to the other side, divide by 6, so negative 1/3. Right? a1, 2 divided by 6 is negative 1/3. a1. And a naught move to the other side, divide by 6. That is a3. And then a4. So a4 is equal to the 3a2 move to the other side, divide by 12. 3 divided by 12 is 1/4 a2. The a1 to the other side, minus 1/12 a1. And 1/2 move to the other side, divide by 12, 1/24 a naught. Right. Next, we did have a2 is equal to negative 1/2 a naught. So negative 1/4, negative 1/2 a naught, minus 1/12 a1, minus 1/24 a naught. All right. Now, negative 1/2 times negative 1/4. Negative 1/2 times negative 1/4 is 1/8 of that. Subtract 1/24 and change that to fraction 1/12, positive 1/12. So negative 1/12 a1 plus 1/12 A naught. Right, so that is A4. Right. So we write the power series for everything, multiply them out, combine like terms, make that equal to 0. So the concept is pretty simple. Power series for everything, multiply them out, combine like terms, and then all the coefficient must be 0. That's simple enough, right? And then we have the solution. A naught, A1x, A2x squared, A3x cubed, A4 x to the 4th, and so on. So that's a standard power series. Now A naught is just A naught. A1 is just A1. A2 is -1/2. A naught x2. A3 is that -1/3. A1 minus 1/6. A naught x cubed. And A4 is that now if we compare to the solution we have on the previous page, A naught A1x -1/2, A naught x squared -1/3, A1x cubed -1/6, A naught x cubed, and then we even have the fourth term. So they actually the same. So we can just take derivative and use the Taylor series, or we write not the Taylor series, the power series for everything, multiply them out, combine like terms, and make them equal. I mean, make them equal meaning equal to 0, meaning all the coefficients have to be equal to 0. By the way, if we want to, we can group everything in terms of A naught 1, and this is -1/2. A naught and -1/6. Factor out the A naught x cubed, and then wait, 1/12 that I forgot here. 1/12. Factor out A naught. Right, and then we have A1 and x. A1 so -1/3 x cubed minus 1/12 A1 factor out x to the 4th. Yeah. So we can write that as two power series representation, and they are linearly independent analytic solution. Right. So of course when we have the coefficient that written as a power series, the calculation could be complicated, but of course it's doable. We just keep doing that. Of course if we want more terms, just write more terms, multiply them out, and have more terms. We can go as far as we want to, but that's the idea. So either we do that. By the way, if we do the derivative like this, when we have a bunch of product rule, that could be complicated. So this is a more doable solution. Right. Very simple. Write a power series for everything. Multiply them out, combine like terms, and all the coefficients must be equal to 0. So that's all we have. And so the point in this section is that P of x and Q of x have to be analytic. So meaning that we can write a power series representation for everything. And from there, we can solve like this for the solution. Right. So the key point here is the point has to be an ordinary point. So there will be a power series representation. And not only that, this section we learned that when we have an ordinary point, we can write a power series solution. And not only we know the ordinary point, we can write the radius of convergence for that power series solution as well. But that's what we do in this section. Equation with analytic coefficients at an ordinary points. Right. As always, thank you for watching. See you in another video in differential equations.